Okay, so when you open this up, what you're going to see is this in front of you, this screen in front of you that says All or Nothing, a case study in muscle contraction. Now these are provided for me. I have a, I guess a subscription, I suppose, would be the closest thing. I have a subscription to this service that provides case studies in anatomy and physiology. I know this is what you wish you had a subscription to. Yes, how exciting, but it's what I like. So let's talk about this. All right, so they set you up as a student, an intern in this particular case, and you are working in a lab of a doctor. This is Dr. Priya Wayne, and Dr. Wayne is a specialist in rare neuromuscular and musculoskeletal disorders. So I'll just read this to you to set it up. And then they ask you a series of questions, and then they present the case studies. So this has to do, you're going to really need to review your molecular mechanisms of muscle contraction. And in fact, some of these, or one of these case studies, one of them in particular, will go into a bit more detail than I really expect you to know at this level. However, that's okay. It's okay for me. I'll explain it to you. Okay, so you're working with Dr. Wayne for the last year. Due to this experience, you've gained a great deal of knowledge about the human body and muscle physiology. Of course you have, as an intern and a student. You're also a college student, which you are. Working with Dr. Wayne has allowed you to gain first-hand experience with some of the material that you're learning in your human physiology course. Just last week, you had to turn in an assignment comparing and contrasting disorders of the neuromuscular system. You learned all about several issues, including myasthenia gravis, Sarin, curare, botulism, and Eaton-Lambert syndrome. These all have to do with, of course, Dr. Wayne's specialty of neuromuscular and musculoskeletal disorders. All right, today, a group of high school students is coming in to tour. Dr. Wayne has asked you to prepare some information about muscles to present to the students. Specifically, Dr. Wayne has asked you to discuss the neuromuscular junction, NMJ, from here on out, referred to as NMJ, skeletal muscle contraction, and explain some of the issues that can occur when signaling between neurons and muscles does not go as planned. One of the things you should keep in mind as you consider this, muscles really are an extension of the nervous system itself. They operate, how muscles contract is very similar to how nerves conduct a signal. Of course, the muscle ends up being the action portion of the neuromuscular system. Right? The nervous system sends a signal. The muscles say, "I got the signal. Now I will do what you told me to do." If it's capable for them to do it. So they are the workers. Muscles are the worker bees. Nerves are the brains behind the project, guiding the muscles, telling them what to do. All right, so they give you a word list, a word bank, with letters A through P. And you're going to be using every one of these. You use every one A through P. Now, some of these are already going to be quite familiar to you. Sodium should be very familiar to you, of course. Myosin, actin, acetylcholine. These should be quite familiar. Motor end plate. Acetylcholine esterase. Now, some of these might not be quite as familiar. Nicotinic acetylcholine receptor. Now, you know what an acetylcholine receptor is, or you should, or you're going to learn right quick what it is. But it's referred to as a nicotinic acetylcholine receptor because it is a particular kind of, that's a pharmacology term applied to certain kinds of receptors that receive certain kinds of neurotransmitters. It's not that important that we know that at this level. However, it is an acetylcholine receptor. Sarcoplasmic reticulum, you should know what that is. Now we get into dihydropyridine receptor and ryanodine receptor. You don't know what those are. I'm going to show you what those are. You're going to learn what they are. But I'm not going to test you on those specific kinds of things. That's a little bit more advanced than what I really want to get into. But the rest of it is exactly what I want to get into. and what you should be learning from the videos and from this case study. All right, moving forward. Now, here is a list of definitions with a blank in front of it. Well, guess what goes in the blank? One of these letters corresponding to the object that is being described. All right, and so here they are. Da, 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 on and on you go, and so you fill in the blank. So you take all the words from the word bank and fill this in. If you don't know what they are, you got to read up on it. All right, now this is one part of it that I will mention to you. I'm not really interested that you actually draw it or write it out in words. This particular exercise, I think this is a very valuable experience. I think this is a very valuable thing to do. As it says, using the sliding filament theory, explain or draw the process of sarcomere shortening. You should really understand that process quite well. Remember, sarcomeres are the active contractile units of a myofibril. And when you string, one sarcomere shortening, you might shorten by, a nanometer or several nanometers or hundreds of nanometers, but that's a very, very tiny distance. But guess what? You string 1,000,000 of these together, or 2 million, or or 1,000,000,000 in a row, in alignment, and if they all shorten that little tiny bit, you get a pretty dramatic shortening. That's what muscles do. When muscles contract, these sarcomeres shorten on a molecular level, and gather them all together, you get muscle contraction, and that whole muscle shortens. That's what a muscle contraction is. This question here is asking you to either draw that out in pictures or write it in words. I think it's valuable to do that. I'm not going to grade you on this, though. I guess let me just state that out front. On this particular thing, I'm not going to grade you. I'm not going to look for your pictures or your descriptions, but you should do it anyway. If you choose to do it on this form, that's great. I'm happily take a look at it. But you should certainly understand this process. Now, the case studies. So this is where muscle contraction goes wrong, goes awry. All right, let's start with Jeff. Jeff Slater. Jeff Slater is a biochemist. He's working in a biowarfare lab at the CDC. Yeah, there really is a biowarfare lab. He's currently working on a project to develop a new neurotoxin and is using sarin as a model substance. Sarin, S-A-R-I-N. Sarin is a poison. Sarin is often used as an insecticide because it paralyzes insects. And if you paralyze the right muscles, they can't breathe or they can't move and they die. Well, it does the same sort of thing in humans, but you have to figure out exactly what it's doing in humans. All right, so here's Jeff. He's working in the lab and the alarms go off, which is never a good thing in a biowarfare laboratory. Jeff accidentally knocks a vial of sarin over and a bit of liquid splashes onto his arm between his gloves and lab coat. All right, so if it's between his gloves and his lab coat, it's on his skin. He starts to feel dizzy, his heart starts pounding harder than ever, and he has shortness of breath. He feels incredibly sluggish and tries to get to the exit. As he approaches the lab door, his muscles cramp up and he falls down and hits his head, knocking him unconscious. His colleague from across the hall happens to see him fall and calls for help. Jeff is given oxygen and taken to a nearby hospital, which happens to have a neuromuscular specialist. Thank goodness for Jeff. The sound of the alarm turns out to have been just routine testing of the new system. Oh great, somebody probably should have told Jeff that. All right, now when you get into a case study, you start to get into, and the first question that they're going to ask in both cases here, in each one of these cases, what they're going to ask you is, what are the symptoms? What are the symptoms that Jeff is experiencing? Symptoms are objectifiable things that a person is exhibiting or experiencing. Now, what I mean by that, let's talk about this. Let's answer this question. What symptoms is he experiencing? Well, he starts to feel dizzy. That's a symptom. His heart starts pounding. Right, okay? Heart pounding. He has shortness of breath. He feels sluggish. Symptoms, his muscles cramp. Now, it's not a symptom that he falls down, but it's because his muscles cramped up that he fell down. Now, of course, he's unconscious at one point in time, so he can't really tell you this stuff, but it's in the description, so we're just going to say that either he said it or somebody else said it. Now, the one thing a symptom is not, when we describe these symptoms, you might say, Jeff felt anxious. Well, he probably did, but he doesn't say that, and it doesn't say anywhere in the description that he felt anxious. You could say that he was worried. He probably was worried, but it doesn't say that. So that's not a symptom in the sense of you want an objectifiable, either something that somebody said or something they exhibited, objectively that you can corroborate either with somebody else or with the patient themselves, right? So don't guess at what a symptom is. It's right there in the paragraph. Those are symptoms. Also, I will warn you, as a clinician myself, one of the things that people love to do, and I'm one of those people, is to jump ahead of the game and say, oh, these symptoms are what explains these symptoms. At first, just accept them as symptoms, right? Just write them down. Don't think too much about it at first. Eventually, yes, of course, we want to be able to explain symptoms through molecular and physiologic mechanisms. Let's see if we can. Okay, now they jump way ahead. What symptoms is he experiencing? Great, we wrote this down. What is the role of ACHE? What the heck is ACHE? You go back, and you see in the list acetylcholine esterase. Okay, get out of the way there. Acetylcholine esterase, ACHE. Acetylcholine, the neurotransmitter itself, is abbreviated AC small h, acetylcholine. And the acetylcholine receptor is NACH. Okay, so we're talking about acetylcholine esterase. One of the things I want to review here is, what is acetylcholine esterase? Well, it's an enzyme. ASE tells you that it's an enzyme. It's an enzyme for acetylcholine. Enzymes for specific molecules break those molecules apart. It could put them together. That's another thing enzymes can do. They can put molecules together, or they can take them apart. In this case, acetylcholine esterase breaks apart acetylcholine. This enzyme is found in the neuromuscular junction between the terminal part of the motor neuron, the membrane, and the membrane, the postsynaptic membrane, which is the muscle membrane, the sarcolemma, where the action potential will transfer and help to generate a muscle contraction. There's a space there called a synapse. That tiny, tiny little gap. In there is acetylcholine esterase. It breaks down acetylcholine. Think about what acetylcholine does. It's released from the terminus of the motor neuron. It travels across the synapse, tiny, tiny little distance, but it's got to row across. It's got to make its way over to the sarcolemma, and it has to attach to its receptor in order for that muscle fiber to contract. If it remained attached to its receptor all the time, it would constantly depolarize the sarcolemma. So you need acetylcholine esterase to break down the acetylcholine to stop the muscle contraction. That's going to be important. Now, I just gave you the answer to that, but I want to make sure that you understand what's happening here, or at least understand to the extent that you can at this point. All right, next up. So Jeff's admitted to the hospital. Dr. Wayne examines him. Jeff is unconscious. He's experiencing some paralysis. So Dr. Wayne orders blood work. Here's the blood work. The thing about blood work, and I'll just simplify this for you, look for the abnormalities. That's why they give you normal range on the right side. The result for Jeff is on the left of the chart here. All right. Now, it's good to review things, right? His blood pressure is normal. Now, You could look at this chart and say, I don't believe that. You have to accept the data that they give you. You must accept it at face value, meaning this is correct. This is factual data as Dr. Wayne got the results. Okay, so his blood pressure is normal. His hematocrit is normal. That's the cellular component of his blood. In fact, some of these things you're going to go, why is that important? What does that do? I don't understand. That's okay. If it's normal, it's normal. You don't need to understand it then. Right? So his hematocrit is normal. His blood glucose is normal. His blood sodium is normal. His blood potassium is normal. His acetylcholine esterase test. Whoa. Okay. 100. 100 simply means 100%. You and I and Jeff, before the sarin hit him, had normal, we have to assume, because Jeff was functioning as a biochemist in a lab and doing his job, so his muscles were likely functioning quite normally. 100 simply means he had 100% of normal acetylcholine esterase activity. And that's what you should have. You should have 100%, and I should have 100%. Everybody should have normal activity. That's normal. Acetylcholine esterase test, he's got 44% of normal. It's way down. All right. His T4 levels, that's just a hormone that comes out of your thyroid gland. It's normal. His there's T3 and T4 is excreted from the thyroid. They're both normal. And they also tell you antibodies for the acetylcholine receptor. They're not present. Right? So normally they shouldn't be present. The second case is going to get into that aspect. All right. So we look at these results. We see, now they ask you, which of Jeff's levels are abnormal? Well, there's only one, but it's a biggie. That one right there. Okay, so you write it down. What is the mechanism of action of sarin or sarin-like chemical? I'm going to leave that to you to determine based on his lab results. What would exposure to a sarin-like poison? Now you have to figure out what does sarin do. I hope you can rationalize and think your way through this and don't have to Google it. I am going to say you can Google it, but I want you to think about this. I want you to imagine what is happening, what's going on here. And I'm going to walk you through it a little bit. Okay, so let's look at some pictures out of your book. Oh, let me blow this up a bit. We'll make this bigger. There we go. Okay, so what this is blown up. This is right out of your book. This is a blown up neuromuscular junction. I mean, blown up as in magnified. Not literally blown up, of course. You have a motor neuron. A motor neuron comes down here. This is myelin, a myelin covering. We're going to learn all about that in the next few weeks. But this nerve comes down, and it has a axon terminal. The end of it, right? The end of the motor neuron expands, and it comes in contact or almost contact with the sarcolemma, and the sarcolemma is the membrane that surrounds myofibrils. Okay, I'm going to move me up a little bit here so you can see a little bit. This is where acetylcholine is kept inside those vesicles. They're called synaptic vesicles. The synaptic vesicles have acetylcholine inside them. They're just waiting for the message to say, go ahead, flood the synapse, row yourself across to the sarcolemma where a receptor is waiting to receive you. That's what this is. Okay? So this whole thing is called a neuromuscular junction. But the part on the sarcolemma, on the muscle cell membrane, that is in contact with the axon terminal has a specific name. That is called the motor end plate. The motor end plate is where the receptors are, the acetylcholine receptors. Right, so stimulus comes down, synaptic vesicles fuse with the end of the axon terminal, the membrane of the axon terminal. That's an active process. That's a process called exocytosis. We talked about this a couple months ago. Exocytosis requires ATP. What that does is the synaptic vesicle with acetylcholine inside it merges with the use of ATP with the axon terminal membrane. That spills out acetylcholine into the synaptic cleft. Acetylcholine, as I say, rows across. It diffuses across, of course, to its membrane, or to its receptor. Acetylcholine receptor over here. It binds there. When it binds, it opens up sodium channels. The more sodium channels you open up, the more likely you are to create what is referred to as depolarization. You open up the sodium channels, there's a lot of sodium outside the cell membrane, there's less sodium inside. Sodium wants to flow down its concentration gradient. If it's high on the outside, low on the inside, it will flow into the muscle cell. The muscle fiber. Muscle fiber and muscle cell are alternate terms for the same thing. And that's what you're looking at right here. All right, so this is what acetylcholine does. Sodium spills in here, and that causes a depolarization of the rest of the muscle cell membrane, the sarcolemma. The depolarization spreads across the sarcolemma, causing more sodium to go into the muscle cell membrane, or into the sarcolemma. And then that has an effect on the inside, which we'll get to. So that's how muscle contractions begin. Now, in that same gap in there is acetylcholine esterase, the thing to break down acetylcholine, which will stop acetylcholine from binding because there's no acetylcholine. It can't bind to its receptor. The flood of sodium will stop because the gates will close. That stops a muscle contraction. So you have, it's not analogous to a light switch, but it has some certain similarities to that principle. Okay, so we go back. So we say, what's the mechanism? That's for you to figure out what would happen if you have exposure to a sarin-like poison. How would that affect the amounts of sodium going into the muscle cell? Okay, that's the next step in the process. Remember, acetylcholine crosses a gap, attaches to its receptor that opens sodium channels. Acetylcholine esterase is used to break down the acetylcholine to take it away from its receptors, to stop the sodium from going in. Within my description, I've answered this question. You write it down. All right. How would exposure to sarin or sarin-like chemical affect calcium levels inside, read this carefully, inside the sarcoplasmic reticulum? Well, let's zoom in a little closer. So I'm gonna go down. There's another, here we go. Okay. This is all in your book. These pictures are right in your book. Okay, again, our motor neuron, our synapse. Here's acetylcholine, crosses the gap. Good. Action potential propagates because now we've opened sodium channels along the sarcolemma. The T-tubules bring that depolarization, that wave of depolarization, closer to the myofibril. All right. As that depolarizes, it causes the sarcoplasmic reticulum, which has calcium in it. Sarcoplasmic reticulum are these blue things. These blue, looks like a net. The blue net here is sarcoplasmic reticulum, and it has calcium inside it. When the wave of depolarization comes through the sarcolemma and down the T-tubule, that causes the sarcoplasmic reticulum to let go of its calcium, to release calcium from the inside of it to the outside. That calcium now bathes the myofibril itself. The actin and myosin, the thin and thick filaments, are now bathed. It's like a calcium shower from above, right? All this calcium floods down onto those myofibrils. We're gonna get to a moment why that matters. So we go back here. How would exposure to sarin or sarin-like affect calcium levels inside the sarcoplasmic reticulum? And why? I want you to rationalize through that. Now you know where the calcium is being held inside the sarcoplasmic reticulum before muscle contraction. All right, moving on. How do the altered calcium levels affect the position of actin and myosin filaments? Here's where you're going to have to review how those actin and myosin filaments overlap and interface with each other. Remember, the myosin has myosin head groups, and they really want to attach to actin, to globular actin chain. But they can't because they're being stopped, they're being blocked. They're being blocked from accessing the specific place on the actin molecule where they want to grab onto. So they're being blocked by these other molecules, and we're going to I'll show you pictures. Let's zoom in. Let me zoom in on that action. Oh well, yeah, again, this is in your book. I'm just running through the slides of the slides that I have. Again, axon terminal. Let me get to the other molecules because I want to show you that. Right. Here's the second part that we talked about to help you to answer those questions. Here's the third part, the action potential. Comes down into the T-tubule, spreads the action potential. Here's the sarcoplasmic reticulum with calcium inside it. Now, I want to show you something. I will come back to the actin and myosin. I forgot about these slides that I had because I really want to show you these slides in your book, of course. In the word bank, there's a couple of words, a couple of receptors that you don't need to know that I told you that you're not responsible for, but I want to show you where they are. They are in this picture right now, but they're not even identified in the picture. But I want to show you where they are. So I have another picture. So this picture, let me open that up. This picture here's the sarcolemma. So this is outside. At the top of the screen is outside the sarcolemma. And then inside the sarcolemma right here, but still outside the sarcoplasmic reticulum. And then if I keep on going, in here, now I'm inside the sarcoplasmic reticulum. This is where calcium is. All right. So the wave of depolarization, the depolarization wave, is going to be coming down the sarcolemma, and that is going to open up this channel. That's called the dihydropyridine site, or dihydropyridine receptor site. All right. So this is where dihydropyridine receptor is. And then inside the sarcolemma, but outside outside the sarcoplasmic reticulum, is another receptor in the sarcoplasmic reticulum membrane called the ryanodine receptor. That's what RYR is, ryanodine receptor. Right. So these two things, these two receptors and channels, are the thing that open up calcium channels to allow the calcium to come out of the sarcoplasmic reticulum on top of your thick and thin filaments. Otherwise, sarcoplasmic reticulum stores the calcium and waits for the signal. And the signal has to be opening up the door here. The door is the ryanodine receptor. And here's the dihydropyridine receptor. So now you know where these are and roughly speaking what they have to do with this whole process. Now there aren't going to be any other questions on these specific components. Okay, so now we can back up. Now we can go back to, as I say, action potential comes down. So this would be the ryanodine receptor. Here's the dihydropyridine receptor. You know that now. They don't even identify it in your book, so that's fine. All right, we move on. Well, that's going to be next. Okay. So now you know where those receptors are. Okay. Now, right, so what the calcium does is, remember, actin and myosin want to get together. They really are strongly attracted to each other, but they are blocked from getting together by a ribbon that runs along the actin chain of tropomyosin. So there's another protein in there. Tropomyosin blocks the place where the myosin head wants to grab onto actin, but he can't grab onto it because tropomyosin's in the way. So tropomyosin is kind of the the bouncer, but the bouncer has or the bodyguard has to have a master, an employer, somebody who tells the bouncer when to get out of the way, and somebody tells the bouncer when to stay in the way. That person is troponin. So troponin can shove tropomyosin out of the way, and then actin and myosin combine. But troponin must have calcium around it to want to move tropomyosin out of the way. So if calcium is there, troponin will push tropomyosin out of the way. Actin and myosin bind. We call that a muscle contraction. We get cross-bridge cycling then. So, how do altered calcium levels affect the position of actin and myosin filaments? You explain it. What needs to happen to Jeff's postsynaptic membrane? Remember, postsynaptic is after the synapse. The synapse is a gap. Anything prior to the gap is presynaptic. Anything after the synapse is called postsynaptic. Okay, what has to happen to Jeff's postsynaptic membrane to remedy his paralysis? Physiologically, what do we need more of and where? That has to do with what effect serin has, and specifically what effect serin has on acetylcholine esterase. Now I want to explain something here too. I think we go on to the next case study. Yeah, I want to explain one other thing. They mention in this that Jeff spasms, right? So his muscles contract very, very hard and he can't control himself and he falls over. That's when he smacks his head. Now they're describing this. They're saying what needs to happen to Jeff's postsynaptic membrane to remedy his paralysis. And you might say, well, I thought he was fully contracted. So isn't he like stiff as a board? You can't stay that way forever. If you open up the sodium channels at the neuromuscular junction and open them up and never close them, eventually the high concentration of sodium and the low concentration of sodium inside the muscle cell membrane equalize. If they equalize, then there's no more influx of sodium. Sodium doesn't want to diffuse in. And so now, instead of being spasmed, you're paralyzed because you cannot generate a muscle contraction anymore. So people generally die of sarin poisoning because their thoracic diaphragm, the muscle that's underneath your lungs that does most of the breathing for you, that becomes paralyzed. They can't breathe. They suffocate. Right? So at first it's a spasm because you're getting this flood of sodium inside the sarcolemma, and then it's paralysis because there's no more, there's no concentration gradient of sodium outside the sarcolemma, inside the sarcolemma. So then you don't generate action potentials and you don't get release of calcium, and so you're paralyzed at that point. There is a way to remedy that. Suggest some things that you can do, remembering what sarin did to acetylcholine esterase. All right, now I know I've kind of guided you and I've given you all the answers. You just have to write them down, but I want you to think through the process because it helps you to understand the molecular mechanisms here. Okay, that's case study number 1 and the initial list. Let's go on to case study number 2. Sandy. Whoops, I gotta move me now. Move me down here. Okay, Sandy. She's a preschool teacher. She's not been feeling well. She's not been feeling like herself. She's been feeling tired. Her coworkers have commented on her droopy eyelids. Additionally, she's experiencing weakness in her arms and her legs. She has difficulty talking clearly. Even her students, parents, have been concerned that Sandy hasn't been looking very happy at work. One day at lunch, Sandy started to choke on her food. Yikes. Causing one of her coworkers to perform the Heimlich maneuver, which, as an aside, is no longer called the Heimlich maneuver. It's called abdominal thrusts because Dr. Heimlich is dead. He's been dead for a while. But his estate wants to get paid for the use of his name. And so I don't know if Heimlich himself wanted that, but his estate wants it. So every time you write down the word Heimlich, you got to pay them some money. At least I don't know if that's still the case, but that's an aside. Now we call it abdominal thrusts. Anywho, while the scare didn't cause any permanent damage, Sandy is convinced it is time to go see the doctor. That sounds reasonable. All right. She tells all this stuff to Doc. Doc does some blood work. As last time, right? So, again, BP, she's okay. Hematocrit, she's okay. Glucose, she's okay. Sodium, she's all right. Potassium, she's okay. Acetylcholine esterase activity test, she's okay. Alrighty. So she doesn't have the same thing going on that Jeff did. All right. T3, T4, nah, we're okay. It's all good. Last one here, antibodies for acetylcholine receptors. Now, antibodies come from the immune system. Your immune system generates antibodies against an invader, or what it considers to be a foreign invader of some kind, and it wants to attack it, just like antibodies for SARS-CoV-2, right? That's the enemy these days. This past year has been a brand new enemy, but it's certainly an enemy. You would like some antibodies against that enemy. For some reason, her body is making antibodies against her own acetylcholine receptors. So this is referred to as an autoimmune problem. And we're going to see that she has a disease that I want you to figure out what she has. Because they're present, you shouldn't have antibodies against acetylcholine receptors. Now you have to start to think, okay, I've got an acetylcholine receptor, I have an antibody against it. I am knocking out my acetylcholine receptors. What effect will that have? All right, symptoms. Again, we got to go into here. Symptoms, droopy eyelids, weakness in her arms and legs, difficulty talking. Now, this whole thing, a symptom isn't not looking happy. That's really not a symptom. What that may be is you can write it down. That's more of an emotion. And emotions are fine to write down too when you're doing medical interviews. But there may be more physiology behind the fact that she doesn't look happy. Now, she starts to choke on her food. She's having difficulty swallowing. Okay, so those are symptoms. Right? What levels from her blood work are abnormal? Again, you look at this whole thing, focus on what's not normal, and there's really only one thing here that we care about that's not normal. How would antibodies against her acetylcholine receptors affect the neuromuscular junction? We kind of went through that with Jeff. What's the acetylcholine receptor for? It's to bind acetylcholine. What happens when it does bind acetylcholine? We went through that with Jeff. If the acetylcholine receptor were blocked by an antibody and acetylcholine couldn't get in there to bind to it, what happens? Or maybe I should describe it as what doesn't happen. All right, antibody receptors. So how would antibodies against the acetylcholine receptors affect the influx of sodium into the cell, into the sarcolemma? So, right, we went through this in these slides. This process. If acetylcholine could not get to its receptor, what happens to sodium? Okay, so you answer that. How would antibodies against acetylcholine receptors affect levels of calcium inside the sarcoplasmic reticulum? So now we're taking you down the chain. If the sodium can't get in, what happens to the calcium? What effect does this have on the actin and myosin filaments? We went through that with Jeff. Now you just have to extend that here in her particular case. Now, what disorder does Sandy have? I will tell you that in the very first paragraph of the specialties of Dr. Wayne, her problem is defined. Right? So you have to go back there, go all the way back, look in that paragraph, and her disease is one of those that's listed. You have to figure it out. Now, finally, using the table below, compare muscle contraction problems faced by Jeff and Sandy to that of a normal person. So what this means is, so you just have to use normal, increased, or decreased. Okay? So you can write out the word if you like. You can just, say N for normal, INC for increased, DEC for decreased, or you can use arrows, a sideways arrow. Now, of course, a healthy person is considered normal. So what would you expect? Well, you'd expect normal. You'd expect acetylcholine esterase normal. Receptors normal. Sodium influx, you would expect we would have normal influx. Sarcoplasmic reticulum calcium release, you would expect that to be normal. Cross bridge formation, you'd expect that to be normal. Frequency of muscle contractions, you'd expect it to be normal. With Jeff, so you have to go through. Would he have more or less acetylcholine? More or less acetylcholine esterase, or the same? And on and on and on. And the same for Sandy. What you're going to see is there are some things that are the same in all cases, and there are other things that are different depending on what their problem was. All right, so this is your assignment. These are the 2 case studies that you have to fill out, and then the final table here. And then you will turn that back into me. You will return that through Blackboard, through the assignments. And each one of these case studies, Sandy's case study is worth 5. Jeff's case study is worth 5. And then then this stuff is just part of it. Okay, so this is what I want you to do. Set yourself the task of finishing this, turning in about a week's time, and I will be looking forward to seeing your responses. If you have questions about this, you can email me or ask to explain some of these things, but this is really in depth into the biochemistry, the molecular biology, and the cellular biology of what happens to get a muscle to contract or relax. What's the process? Now, you should also remember this happens in about, muscle contraction takes about 1/200th of a second, maybe 1/100th of a second, depending on the kind of muscle. So, 1/100th, we'll just make the math easy. 1/100th of a second, you can get a muscle to contract and relax. A muscle fiber, contract, relax. 1/100th of a second. It happens very rapidly. It takes a long time to describe it, but it happens very quickly. Thanks for your attention.